Standard probabilistic language models face a semantic chicken and egg problem. To learn the relationships between words, they require initial values to begin their calculations. But before reading any text, they lack linguistic knowledge to inform those values. The common solution is to assign random values to every token. By starting from zero, the system relies on massive computational overhead. It begins ingesting enormous quantities of text, utilizing sheer brute force to continually adjust millions of internal weights until statistical patterns begin to take shape. Over time, this intense statistical exposure does work. Meaningful semantic relationships emerge from the noise. However, the architecture of those relationships is compromised by the way they were built. The learned information becomes highly entangled. A single semantic concept is weakly distributed across thousands of overlapping dimensions, holding no interpretable meaning. During inference, piecing these fragments together requires massive computation. The Aurora project rejects this. We eliminate random initialization to shrink the search space. We already possess decades of rigorous human knowledge about how language functions. By embedding that knowledge directly into the starting state of the model, we bypass the computational drag of entangled, uninterpretable representations. This approach is driven by Project Genesis, known internally as Mariposa. Its foundational premise is that we can convert established linguistic, phonetic, and grammatical research into an organized mathematical seed for the AI. Instead of guessing, the system assigns basic, explicitly defined semantic properties directly to individual characters. These characters act as atomic tokens, the absolute bedrock of the model. We encode atomic tokens across specific linguistic dimensions, functioning as a vowel or consonant, open or closed sound, and precise physical articulation. Distributed within a ternary fractal structure, every base character possesses a unique, stable, mathematically interpretable tensor at system boot. In early trials, the sequences generated by this initialized system didn't immediately form perfect dictionary words. However, they consistently capture real phonetic regularities. When read aloud, the output sounded like plausible, structurally sound language. Grounding atomic tokens in linguistic axioms ensures the model begins with a consistent map of physical phonetic properties. This stability replaces initial statistical noise, allowing the architecture to build higher-level coherence upon a consistent phonetic foundation. With stable character tensors established, the next requirement is a mechanism that allows the system to ascend. It needs to autonomously build coherent morphological and grammatical structures out of those base tokens. Fortunately, written language provides a roadmap. It naturally contains visible signals that dictate structural boundaries. Spaces separate words, punctuation divides sentences, and line breaks isolate paragraphs. We treat these boundaries as signals of closure. When the system encounters a word bracketed by spaces, it receives a clear structural target. The AI doesn't know the optimal internal decomposition yet, only that the bounding box represents a finished linguistic unit. The operational directive is strictly mathematical. The system must guess and test different internal segmentations of the characters until it discovers an internal structure that perfectly reproduces the closure signaled by the boundary. Linguistic closure provides the necessary constraint. It forces the AI to solve the internal math and construct complex tokens on its own, without engineers explicitly handing it the correct internal structure. To reach a stable closure state, the system rapidly iterates through combinations of syllables and morphemes, testing a logical segmentation. However, the system could easily test an awkward, arbitrary grouping of letters that achieves a trivial local closure for this specific word. To filter out false positives, Aurora relies on a strict threshold for sustainable coherence. True knowledge, K of X, requires both closure, C of X, and generalization, G of X. Local closure solves the immediate case, but for a structural grouping to be classified as generalized knowledge, that exact internal relationship must prove itself reusable across other words. This requirement powers Aurora's dynamic dictionary. When a substructure successfully closes multiple words, the dictionary categorizes it as reusable, elevating it up a prioritized hierarchy. Conversely, arbitrary segments with only accidental coherence fail to generalize, losing priority until they are discarded. This dynamic culling process is highly efficient. First, it explicitly teaches the system what structures actually exist as reliable rules. Second, the priority ordering teaches the system exactly in what order it should search for these structures when encountering new data. The dynamic dictionary acts as a self-optimizing engine. By solidifying reliable rules, it reduces the mathematical combinations the model must calculate, driving down the computational cost of future learning. There is a critical caveat to this process. Achieving structural or grammatical closure at a local boundary does not automatically guarantee that the resulting sentence makes logical sense. Consider the test phrase, La mesa devora ideas cuadradas. The table devours square ideas. Aurora evaluates closure across multiple dimensions simultaneously using formula E of x d n. A syntactic scan passes, as the sentence has a valid noun, verb, and object. However, a semantic scan instantly flags an anomaly because a table lacks the biological capacity to devour. By tracking these evaluations independently, the architecture allows higher, more complex structural levels to audit and correct provisional assumptions made at the foundational levels. Robust coherence in the Aurora system never hinges on a single passing metric. A semantic structure is only finalized when multiple distinct dimensions mathematically converge and hold up under simultaneous scrutiny. Because this dimensional logic relies on abstract mathematics rather than hard-coded rules, the entire Aurora architecture is scale invariant. The exact same fundamental operator is applied uniformly. Boundary detection, mathematical discovery, and generalization dictate the flow from characters to syllables to words, phrases, and high-level concepts. The mechanism iterates upward, building density and complexity without changing the underlying mathematical constraints. This means engineers do not need to explicitly program complex grammatical categories into the model. Syntax and grammar emerge naturally simply because they represent the most mathematically efficient structures for the system to explain closure across millions of diverse phrases. Standard probabilistic models are designed to preserve heavily entangled statistical patterns, requiring immense power to interpret weak relationships. Aurora methodology targets a different end state. By utilizing generalization as a strict evolutionary filter, the system crystallizes only highly reusable, interpretable structures. It turns raw data into complex, stable tokens. In this system, the dynamic dictionary functions as the neural architecture, simultaneously representing, operating on, and transmitting knowledge through a single unified structure. Project Genesis operates on a specific mechanical principle. Coherence is never imposed from the start. Real semantic understanding within an AI is earned through the hierarchy of language. It is born from local linguistic signals, tested through rigorous internal discovery, and sustained strictly by its ability to generalize.